Hello there, welcome to the June 2018 paper. Here we're looking at question 8. Question 8 is a double proof by induction question, my favourites. So, first of all we want to prove that 5 minus 8 to 2 minus 3 to the power of n is equal to this expression here. Okay, let's get started. So part I is going to be prove true for n equals 1. So 5 minus 8 to minus 3 to the power of 1 is equal to 5 minus 8 to minus 3. And then if we do the same substituting in for this expansion here, so it would be 4 times 1 plus 1 minus 8 times 1, 2 times 1, and then 1 minus 4 times 1, that will give us as well 5 minus 8 to minus 3. So therefore, left hand side is equal to right hand side for n equals 1. Okay, next step, let's now assume true. So assume true for n equals k. So therefore, 5 minus 8 to minus 3 to the power of k will equal 4k plus 1 minus 8k, 2k, and 1 minus 4k. Now that we assume true for n equals k, we now have to do the main bit, which is prove true for n equals k plus 1. Prove true for n equals k plus 1. So I always like to do a WTS, a want to show. So what I want to show in this part here is that 5 minus 8 to minus 3 to the power of k plus 1 equals bracket 4 bracket k plus 1 minus 8k plus 1 2 bracket k plus 1 and then 1 minus 4 bracket k plus 1. Okay, that's what I'm looking to show here. Let's put that in a little box and let's start with the left hand side. So the left hand side is equal to 5 minus 8 to minus 3 to the power of k plus 1. Okay, let's split this into a multiplication. 5 minus 8 to minus 3 to the power of k times this matrix again. We're kind of inversing the rules of indices there, that when you have two indices that are adding together, you multiply the same base and you would then add your powers. So now I'm going to use my assumption step here, because I've now got my matrix to the power of k. So this is going to equal 4k plus 1 minus 8k, 2k, and 1 minus 4k. And that's going to then multiply by 5 minus 8 to minus 3. Okay, so let's now go ahead and do this multiplication of one matrix by another. So it's going to be, let's leave ourselves lots of space to do this. 4k plus 1 times 5, so that would be 20k plus 5. And then move across and down, minus 16k. Moving on to the top right cell, 4k plus 1 times minus 8, so that would be minus 32k minus 8, and moving across and down, that would be then plus 24k, double negative there. Moving on to the bottom left now, it's going to be 10k, and then moving across and down, so it would be plus 2 minus 8k, and then the bottom right one, it's going to be 2k times minus 8, that's minus 16k, and then it's going to be minus 3 plus 12k. Okay, let's now simplify all of this, and we're looking to now start to head towards the right hand side of our want to show. So it's now going to be 4k plus 5. The next one's going to be minus 8k plus 8. The next one's going to be 2k plus 2. And the bottom right one's going to be minus 4k minus 3. And then the final bit is just to make sure that all of these things from our 4 different points on our matrix here will equal this right hand side of our want to show. So is the top left hand cell going to equal 4 brackets k plus 1 plus 1? Yeah, that will. That's good. The next one is going to be minus 8k plus 1. It's a minus there. Have I done my expansion correct? Just need to double check this. So that's going to be this one times this one. Oh no, it's minus 8. Oh sorry, I copied it over wrong. So it's a minus 8 there because it was a minus 8 here. So yes, that is right now. So it's a good way of checking that what you've done so far is actually correct. The next one is going to be 2 brackets k plus 1. Yeah, that's good. And then the next one's going to be minus, so 1 minus 4 brackets k plus 1. Let's see if that's true. It's going to be minus 4k, yeah, good. Then it's going to be minus 4, but then plus the 1 at the start, yeah, minus 3. So there we are, equals the right hand side. So there we are, we've now proven step 3. And now the final bit is step 4, and step 4 is our conclusion. So the conclusion is, as we have proven, hopefully my pen is not going to start glitching here, as we have proven true for n equals 1, and assuming our theorem true up to n equals k, we have shown our theorem true, theorem also true for n equals k plus 1. Therefore, then we'll restate our theorem. 5 minus 8, 2 minus 3 to the power of n does equal 4n plus 1 minus 8n, 2n, 1 minus 4n, for n existing in the z plus. We haven't proven it true for any other values of n, just for the values of n existing in the z plus. And I've actually seen examiners deduct a mark if you miss just this bit here. So make sure you don't miss that bit there. That's almost effectively worth 1 mark just itself. So make sure you write your full conclusion with full detail, otherwise you're missing out on silly marks when you've done all the good mathematics to go alongside it. So let's now move on to part B. Okay, so part B is proved by induction for the n existing in these positive integers that f of n equals 4 to the power of n plus 1 plus 5 2n minus 1 is divisible by 21. Okay, so let's prove it true for n equals 1 then. So f of 1 is going to equal 4 to the power of 2 plus 5 to the power of 2 times 1 minus 1 is 1, so that's going to be 16 plus 5 equals 21. So tick. Good. F of 1 is divisible by 21. Then we prove, so do part 2, so assume true for n equals k. So we can assume that f of k equals 4 to the power of k plus 1 plus 5 to the power of 2k minus 1 is divisible by 21. Okay, now moving on to the important step 3 here. So, prove true for n equals k plus 1. Now what we want to show here is that f of k plus 1, which is 4 to the power of k plus 2 plus 5 to the power of 2k plus 1 is divisible by 21. Okay, so let's start. This is what we want to show. Let's start with f of k plus 1, which is equal to 4 to the power of k plus 2 plus 5 to the power of 2k minus 1. Plus 1, sorry. Now, what we want to actually use at some point is f of k. So what I suggest you do first is reduce your powers down to what they were in f of k. So I'm going to split this into 4 times 4 to the k plus 1. So that's 4 to the k plus 1, so splitting out the indices there. I could combine them back again by adding the indices. And with the second one here, it's going to be 5 squared times 5 to the 2k minus 1. So now the powers have been reduced down to the f of k, because I need to use f of k at some point, so it's important I get those back down. So, and I could show that clearly this first line is equal to the second line by adding the powers back together. Let's now factorise. So it's going to be 4 brackets 4 to the k plus 1, okay, and then 5 to the power of 2k minus 1. Okay, now what you're probably thinking is that the second line here is clearly not equal to the third line. If I expand, I've got 4 times 4 to the k plus 1. Yeah, the first bit's fine, but the second bit's clearly not fine. It's just 4 times 5 to the power of 2k minus 21 from the second line to the third line. So I've not got enough 5 to the power of 2k minus 1s. I need to add on. If I've got 4 already and I want 25, I need to add on 21 lots of 5 to the power of 2k minus 1. And now what we can see is that we have two things that are going to be added together that are both multiples of 21. This part here is a multiple of 21, divisible by 21 from the assumption and this bit here is divisible by 21 from a multiple of 21. Okay, so therefore now we just need to write a little sentence saying that the addition of two multiples of 21 is also a multiple of 21. So as the addition of two multiples of 21 is also a multiple of 21, f of k plus 1 is equal to a multiple of 21. And I've changed the terminology here. I've stopped using divisible by 21 and started using a multiple of 21, but that is equivalent. So we've shown that the right hand side, we've shown that this want to show is true now. Now let's move on to part 4 for the conclusion. So the conclusion is, as we have proven our theorem true for n equals, so as we have for n equals 1, and assuming our theorem true for n equals k, we have shown our theorem true for n equals k plus 1. Therefore, by induction, f of k, so f of n rather, because we go back to the n's, don't we? F of n equals 4 to the power of n plus 1, plus 5 to the power of 2n minus 1 is, pen is really glitchy today, is divisible by 21, and you've got to make sure you write for n existing in z plus, because if we put n as a different value like 3 over 2 or pi or something like that, it's probably not going to be a multiple of 21. So there we are, that's the answer to this question here. We've now proved question 8b, 12 marks in total, 6 marks for each of those proof by inductions, and there we are, that's the answer for question 8. Let's now move on to question 9.